Yes, good afternoon, students. So today I will discuss gate switch circuit. So generally, whenever we will just discuss regarding this converter circuit, whether that will be line commutated converter or voltage source converter, right? Whether that will be line commutated converter or voltage source converter. In both of the cases, we are basically using bridge converter, right? And that bridge converter are known as grades bridge circuit. There are two types of the converter. There are two types of the converter. One is LCC, that is the line commutated converter, and second is VSC, LCC and VSC, line commutated converter and voltage source converter, right? In both of that, we are using this bridge circuit or bridge converter, and these bridge converter are known as grades bridge circuit or grades bridge converter. Now, whenever I am talking about LCC, that means line commutated converter, in that particular case, this input to the bridge circuit can be fed from the transformer winding connected either in star or in delta, because here we are basically dealing with three-phase supply, right? So in three-phase supply, we need three-phase input. So in that particular case, either we may utilize this star type connections, or we may use delta type connections to supply input across this circuit, right? Input across this circuit. Now, the converter transformer, that means whatsoever I am saying, that here across this input we are either connected this A, B and C through the star type connections, or we may supply these three inputs with the help of delta type connections, right? That transformer which is used to supply this grades bridge may be able to serve three different purposes. May be able to serve three different purposes. First is galvanic separation between AC and DC side, right? So if I am just saying that in journal, if here, let us suppose this is your star type, right? And it's this secondary is delta type, right? So this will be just connected here, B, C and A. You may interchange these connections. So in either that will be single phase transformer, or that may be three phase transformer. Primary and secondary of the transformer are isolated from each other, right? What is the basic principle of the transformer? Basic principle of the transformer is electromagnetic induction, or Faraday's laws of electromagnetic induction, right? So that means there is no physical connections between primary and secondary of the transformer. There is no physical connections between primary, this is your primary side of the transformer, this is the secondary side of the transformer. So there is no physical connection between primary and secondary side of the transformer. Now on this side I am talking about DC side, on input side of this transformer, that will be the AC side. So what will happen? Galvanic separation between AC and DC side, because they are not physically connected with each other. So there is this galvanic separation between AC and DC sides. Second purpose which this transformer will be able to serve, that is voltage transformation between AC and DC network, right? So obviously this voltage will be transmitted to this Graves bridge circuit with the help of this three-phase transformer. And third is adjustment of the applied AC voltage, adjustment of the applied AC voltage with the help of OLTC, that is on load tap changing device, right? Adjustment of the applied AC voltage by using OLTC, on load tap changing device, right? So three different purposes are there which this transformer which is used to supply this Graves bridge will be able to serve. First is that galvanic separation between AC and DC side. Second is voltage transformation between AC and DC network. And third is adjustment of the applied AC voltage by on load tap changer. Right. Now, one thing that is very important, auto transformer is a device. I think you must be aware with the device auto transformer. It is a single winding transformer with the help of which I will be able to change the voltage at any instant, right? Auto transformer is a device, is a single winding transformer. In ordinary case, we are using two different winding, right? But in case of the auto transformer, we are using only single winding. That means we are serving the both of the purposes, that is the purpose of AC winding as well as the purpose of this primary winding and secondary winding with the help of same single winding and with the help of that tap changer. Now, why I am saying this? If you see the purposes to use this transformer, that are three purposes. One is galvanic separation between AC and DC side, that cannot be served with the help of auto transformer because there is one winding in case of the auto transformer. So there is no galvanic separation if we are utilizing auto transformer in place of this ordinary three-phase transformer, right? So what will happen that if I am talking about other two purposes, that is first, one is voltage transformation between AC and DC side, and second is adjustment of the applied AC voltage by OLTC, right? Both of these purposes may be solved with the help of auto transformer. That means purpose number 2 and purpose number 3. Purpose number 2 and purpose number 3 may be solved with the help of this auto transformer, but galvanic separation cannot be provided in case of auto transformer. So that's why this auto transformer cannot be replaced this LCC, this ordinary transformer in case of LCC, line commutated converter. Because if we are just using auto transformer, then there is no physical separation between primary and secondary of the transformer. So in case of fault on the primary side, secondary sides will also going to be effective, And see here, secondary side of the transformer is directly connected with grades bridge, right? So this is the reason why we are not replacing this ordinary transformer, ordinary three-phase transformer with the help of that auto transformer. We are not going to replace this with auto transformer, because in case of the auto transformer there is a single winding and we are not able to provide galvanic separation between AC and DC side. Right, now come to this circuit diagram. In this case, S1, S2, S3, S4, S5, S6, these 6 are the switches. These 6 are the switches number in the order in which they are turned on. There are 6 switches and its number in which they are just going to be turned on, right? In case of LCC, because today I will discuss only LCC, in case of LCC, these switches are made of thyristor, SCR, right? These switches are made of SCR. These are not made of diode, inner diode, or any other types of the semiconductor device, right? Here we are using thyristor valve, whereas in case of the VSC, that means voltage source converter, we are using IGBT in place of thyristor valve. In case of LCC, we are using thyristor valve. In case of VSC, we are using this IGBT, right? Yes, so regarding the analysis part of the grades bridge, here we are just neglecting this overlapping condition, right? So in case of the LCC, line commutated converter, grades bridge is connected to 3 balanced sinusoidal voltage sources, right? 3 balanced sinusoidal voltage sources on the AC side and a constant DC current source on the DC side. Here 3 balanced voltage sources on the AC side and constant DC current source on the DC side. Now what will happen? Each of these switches, that is S1 to S6 in grades bridge, are made of series connected thyristor devices, because here we are dealing with high voltage, right? Because we are applying this for HVDC transmission. This grades bridge may be just used to connect with the HVDC transmission line. So that's why we are just utilize number of thyristor in series, so that we will be capable to tackle that high voltage. If we want to increase the current rating of the device, we will have to connect number of devices in parallel, right? And if we want to increase the voltage rating of the device, we will have to connect that number of devices in that series. Now we are already aware with the description of the SCR. In SCR there are, as far as SCR is concerned, what is SCR? Silicon control rectifier. silicon control rectifier, right? So here it is PN, anode, cathode, and here it will be in terms of its symbolic representation, anode, cathode, and case. Right. So thyristor is a three-layer, three-junction, and three-layer, three-junction, four-layer J1, J2, J3. Four-layer, three-junction, three-terminal device. Four-layer, three-junction, three-terminal device, and name of the terminals are anode, cathode, and gate. Right? Anode, cathode, and gate. This is regarding the SCR. In case of the Grates bridge, we are using SCR as a switches. Right? So, in this case, what will happen? We are using that this second diagram. This is your diagram 1 or figure 1. This is your figure 2. Now, in figure 2, this will explain you timing diagram of the conduction time, right? Whereas this figure 1, you see your figure 1 is LCC. Figure 1 is LCC, line commutated converter, and figure 2 is timing diagram of LCC Grates bridge, right? So in this case, you will see we are just dividing the total 360° into 6 number of the interval. We are dividing the total into 6 number of the interval, right? During the first interval, as switch 2 and 3 will conduct. Switch 2 and 3 will conduct. During the second interval, 3 and 4 will conduct. During the third interval, 4 and 5 will conduct, and next 5, 6, 6, 1 and 1, 2. Right. So during each interval, during each case, number of thyristor conducted are equal to 2. During each interval, 2 number of the SCR or thyristor will conduct. Rest 4 are under the silent condition. Right. And the duration of the conduction is 60°. Duration of the conduction is 60°. 0 to 60, 120, 180, 240, then 300 and 360. This complete 360° will be divided into 6 number of the parts, as right. 360, one complete cycle will be consist of 360°, and this 360° will be just divided into 3 number of the parts, that 6 number of the parts, right? And that 6 number of the parts will be each consist of 60° each, right? So one thing more, during this condition, what are the voltages across the device that may be seen by this sequence. So this sequence will give you, this will be between valve conducting, right? Here it will be valve conducting, and second is voltage phase. Which valve is conducting and which phase is there? V phase. So interval, there are 6 interval: 1, 2, 3, 4, 5, and 6. Right? There are 6 interval. During first interval, 2 and 3 will conduct. 3, 4, 4, 5, 5, 6, 6, 1, and 1, 2. So in each of the interval, there are 2 valve conducting simultaneously, or 2 thyristor conducting simultaneously. In first interval, 2 and 3, 3 in second interval, 3 and 4, then 4 and 5, 5 and 6, 6 and 1, 1 and 2. Right? So during the first phase, this is the DC bus voltage during each interval. DC bus voltage during each DC bus voltage during. Now this sequence will be taken from the that timing diagram. During each interval, so during the first interval, first 60°, the voltage is EBC. Then during the second interval, the voltage is EBA. Then during the third interval, the voltage is ECA. Then during the next interval, the voltage is ECB. Then during the interval when 6 and 1 are conducted, that is EAB. And during the last, the voltage available across the bus is EAC. So these are the bus voltages, DC bus voltages across the converter for each of the 6 interval. Right? Now, what will happen? I am just considering EBA, the voltage across the valve S3 is EBA, voltage across valve S3 is EBA, right? And this will be represented by EBA is equal to root 2, EBA is equal to root 2 ELL sine omega t, right? So EBA is given by this, the voltage across the switch S3, and this is negative for omega t less than 0. This is negative for omega t less than 0, right? EBA is given by root 2 ELL sine omega t, and it is negative when omega t is less than 0, and it becomes positive when omega t is greater than 0. It will become positive. Fine. So when this omega t is less than 0, this EBA is negative, and when omega t is greater than 0, it will be positive, right? So if we are considering this voltage EBA by delay angle alpha, as we have taken it in that timing diagram, alpha plus 60 like that. So if we are taking this EBA by a delay angle alpha, applying a gate pulse at omega t is equal to alpha, so in that case, this EBA will become EA, EB and EC. EA, EB and EC. EBA will become EA, EB and EC. This will be root 2 by 3 ELL sine omega t plus 150 degree, right? Then EB is equal to root 2 by 3 ELL sine omega t plus 30 degree, and EC is equal to root 2 by 3 ELL sine omega t plus minus 90 degree. So these are the three equations. These are the three equations for EBA. Three equations for EBA if we are considering this equation in term of alpha, right? And it is assumed that delay angle is constant in steady state. It is assumed that alpha is, that means alpha is delay angle. So alpha is constant in case of DC. Yes. So now we will discuss what is the voltage available across the wall during its conduction, right? So here we will see these are the, we are already seen, we will divide the total interval into 6 number of the parts. We will divide the total interval into 6 number of the parts, right? And what are the conducting valves here? Conducting valves during the interval 1, this will be 2 3, then next 3 4, 4 5, 5 6, 6 1 and 1 2. So during each interval, these thyristor or switches will conduct. During the first interval, thyristor 2 and 3 will conduct. Then during the second interval, 3 and 4 will conduct. Then 4 and 5 will conduct. 5 and 6 will conduct. 6 and 1 will conduct. And during the last, 1 and 2. And again after this, your cycle is going to be repeat. Right? So after that, DC voltage. So DC voltage. So during the first interval, this will be root 2 ELL sine omega t plus 60 degree, right? Root 2 ELL omega t plus 60 degree, right? Then during the second interval, because we are taking the sixth number of the interval, so this will be root 2 ELL sine omega t minus 60, 60 minus 60, only omega t. Then for the interval 3, when diode 4 and 5 are conducting, your DC voltage will be root 2 ELL sine omega t minus 60 degree. Then root 2 ELL sine omega t minus 120 degree. Right? So each will be just departed from the first one at an angle of 60 degree. Right? Because in timing diagram we had already seen there is a phase difference of 60 degree, or each of the valve pair will conduct for 60 degree time interval. Right? So next is root 2 ELL sine omega t minus 180 degree. Then root 2 ELL sine omega t minus 240 degree. So these are the value of the DC voltage which will be just applied across this valve combination. Then after that, I'm just considering that for the voltage across valve 1, voltage across valve 1, this is new because that I had already discussed during the previous part of this lecture, right? So here this will be EAB. EAB already we had seen when diode 2 and 3 are conducting, voltage across the valve is EAB. EAB is equal to minus root 2 ELL sine omega t, right? Then after that, during the second interval, again, because during the first 120 degree, this will be same. EAB is equal to minus under root 2 ELL sine omega t. During the first 120 degree, voltage across the valve is same. During the second 120 degree, that means during the 240 degree, voltage across the valve is same. And during the third 120 degree, voltage across the valve is again same. Voltage across the valve will change after each 120 degree cycle, right? So here during the first 120 degree, this will be negative voltage minus 2 ELL sine omega t. Then during the next two, that will be EAC, that will be minus under root 2 positive under root 2 ELL sine omega t. Then again EAC is equal to root 2 ELL sine omega t, right? During the first two interval, that will be negative voltage available across the valve, right? Valve 1. During the second 120 degree interval, that means from 121 to 240 degree. 121 to 240 degree, this voltage across the valve will be positive with the same dimension. During the first 120 degree, the voltage across the valve is negative with the magnitude under root 2 ELL sine omega t. During the next 120 degree interval, voltage across the valve is positive with the same magnitude as that of the previous. That means root 2 ELL sine omega t, right? And now see, it is the important. during the last two interval, that means from 241 to 360 degree, right? From 241 to 360 degree interval, what will happen? Your thyristor valve 1 will conduct, right? During all that upper 4 section, no thyristor valve 1 will conduct, all other 4 will conducting, right? During the interval 5 and interval 6, thyristor valve 1 will be conducting, so voltage across that will be 0. Whenever diode will conduct, it will, oh sorry, thyristor will conduct, it will be act as equivalent to short circuit or on state switch. So whenever it will be act as on state switch, during this condition, voltage across the device that will be 0, because it's anode and cathode, both will be at the same potential, anode and cathode, because once device will here interval during the interval 5 and interval 6, during the interval 5 and interval 6, that SCR1 or thyristor valve 1 will conduct. So whenever it will conduct, your device will be act as a short circuit. So your anode and cathode will be at the same potential. There will be no potential difference. So during that condition, voltage across the valve that will be 0. During the first 120 degree interval, the voltage is negative. During the second 120 degree interval, the voltage is positive. During the third 120 degree interval, voltage across the valve will be 0. In the similar pattern, you may calculate the voltage for other devices, right? For the valve 2, valve 3, right? So this is only the criteria with the help of which you may be able to see what is the voltage available across the valve and what are the DC voltage applied. Yes. So in that DC voltage waveform, in this Grade's bridge analysis, this DC voltage waveform contains a ripple, right, whose fundamental frequency is 6 times, the supply frequency, right? Fundamental frequency whose that ripples is having the fundamental frequency of ripple is equal to 6 times the supply frequency, right? So here this can be analyzed in Fourier series, right? And contain the harmonics of the order of h is equal to 6n. H is equal to 6n, where n is an integer, right? The harmonic in the DC voltage can be given by VH is equal to under root of AN square plus BN square divided by under root 2 AH square plus BH square divided by 2, right? This AH and BH may be calculated from that Fourier series AH is equal to AH is equal to 1 upon pi integrations alpha within the limits alpha to alpha plus 2 pi, right? So VD cos H theta cos H theta d theta, right? Cos H theta d theta, and BH, I think you must aware with this AH and BH generally in there, that will be AN and BN. In case of Fourier series, that will be AN and BN, because here we are dealing with harmonic, so that's why N will be replaced by H. So AH is equal to 1 upon pi integration alpha to alpha plus 2 pi alpha to alpha plus 2 pi BD cos H theta d theta, and BH is equal to alpha plus 2 pi BD sin H theta d theta, right? AH is the cos of the component and BH is the sine of the component, right? So it can be shown that the RMS value of the Hth order harmonic in DC voltage is given by VH is equal to RMS value will be given by VH is equal to VD naught into VD naught into under root 2 over H square minus 1 under root 2 over H square minus 1 into 1 plus H square minus 1 plus H square minus 1 into sine square alpha H square minus 1 into sine square alpha, its under root, that will be the RMS value of the Nth order harmonic in DC voltage. This equation gives VH is equal to RMS value of Nth order harmonic in DC voltage, right? AH and BH that may be calculated by using this Fourier series expansion, and value of the RMS value of the Nth order harmonic in DC voltage that may be given by this equation VH is equal to VD naught under root 2 H square minus 1 into 1 plus H square minus 1 into sine square alpha, that bracket term under root. So I am taking that as 1 by 2 power 1 by 2. So this is the end of the lecture. We will meet with new topic in the next lecture. Thank you.